Okay, part two. Let's take a look at this again. We have the titration between ammonia and strong acid HCl. And of course, it will produce ammonium ion and water. Okay, so if you look at the titration curve, the solution that is in the beaker or in the flask will be the ammonia. Okay, and now at the beginning, you didn't add any acid yet, just ammonia. And you know ammonia is basic. So you can actually calculate for the pH of the solution before the titration by using the Kb of NH3. Um, and then, so now, as you start to add the hydrochloric acid, you can see that some of the ammonia will start to react with the H plus and produce ammonium. So there will be the depletion of NH3 and that NH3 being converted to the NH4. So you can see that the pH starts to drop, and then this point right here, okay, you will have the NH3 and then H4 plus ammonia and ammonium coexist in the solution. So anytime when you have the acid and its conjugate base, again, you have the buffer. Okay, and then what happened at the half equivalence point? Half equivalence point, that means that half of the ammonia, let's say if you start with 1 molar of NH3, okay, and then it react with half of it is gone because half of it is used up to react with the H plus. So that means that a 0.5 of molar of NH3 will be gone because it will have to react with H plus. So at that point, at this half equivalence point, you're gonna have half molar of NH3, and then you're going to have half molar of NH4. So same concentration again. So essentially this is equal. pH will be equal to pKa. Now the pKa is a pKa of NH4 plus now ammonium. Okay. And then that's the value. Another point is that I want to point out, how do you know that is half equivalence point? Look over here, you see this is the equivalence point. Let's say the volume is around 100. At the half equivalence point, how do you spot it? It's going to be, the volume is going to be 50, half of the volume that it needs to reach the equivalence point. And you can see here the half equivalence point, the pH is around 9.26. Okay, so, and then at the equivalence point right here, again, you don't have NH3 left. All you have is NH4. And then you can find the pH just simply by using the ammonium ion. Let's move down a little bit. How do I? Okay, can't move up. Okay. Okay, now let's take a look at this problem. What is the pH of solution at the equivalence point in the titration of 100 milliliter of ammonia? Okay, ammonia, and then with the, I think this is 100 milliliter of HCl. Yeah, it has to be equal. Okay, so at the equivalence point, that means that the mole of the base and the mole of the acid has to be the same, right? Equivalence point. So if you started with 0.01 mole of the base, you're going to have to use the same number of mole of the acid. So at the equivalence point, you will have none of the reactant left. All of them will be converted to ammonium. So now, so the number of mole would be 0.01, but the concentration would be different because the volumes are additive, right? So you started 100 milliliter of ammonia. This is what you started with, 100 milliliter. But now, as you keep on adding the HCl, at the equivalence point, you're going to have to add 100 milliliter of HCl. So the volume at the end is going to be 200 milliliter. right? So now, if you want to find the concentration of ammonium, you have to divide mole by the volume, which is zero point 0.2. So this is why we have the concentration of ammonium, which is equal to 0.05 molar. You want to find the pH? Okay, here we go. So you have the concentration of ammonium. You don't have any left at the equivalence point. But you have to understand that this thing is a weak acid. It will ionize. How much? X. And you can use the Ka of ammonium to find the concentration of these two species. So let's say this X ammonia, X hydronium, divide by 0.0500, subtract by X. Approaches 0. Okay, do the math. X will come out to be 5.3 times 10 to the negative 6 molar. So now since this X represents the concentration of the hydronium, negative log this value, pH come out to be 5.28. And then that's exactly what you see here at the equivalence point. Okay. Now, we already talked about it. We did the experiment on this, but I just want to re-emphasize again that the indicator that you use in the lab is actually it has an acid-base properties, a weak acid, weak base. For example, like this is the structure of phenolphthalein that you use. This is the structure of protonated phenolphthalein. You see that it has the H plus over here. Okay, and then now once you take out the hydrogen, so this in the basic solution, the hydrogen gets taken out. The structure shifts a little bit, okay, from this structure to this structure. So this is why it is changed from this colorless to pink color, colorless to pink. Okay, so now when you want to pick the indicator for the reaction, you want it to be change. You want it. What you want to pick is you want to make sure that the concentration of the acid and its conjugate base form are equal. The concentration are equal. Basically, you want the pKa of the indicator to be equal to the pH where your equivalence point is going to be. So because that is where it starts to change the color. Oh, okay. So now let's take a look over here. There are here. You see here. This is where it changes color. Where um when the concentration of the base and the base and the conjugate acid are equal. That's where you want it to be. And over here is a selection of different types of indicators that you can use at the different pH range. It depends on what type of titration you're doing. So phenolphthalein here, the pH is around, the pKa is around 9. And then the one that we use is methyl red. Methyl red is over here. This is another one that we use. Okay, and that's it.